Hello guys, this is 6.3. We're looking at a fundamental theorem of calculus to find definite integrals. Now we actually had some experience with definite integrals is the represents the area under the curve between the lower bound and the upper bound of the x values, right? So in this section, we're going to use what we learned in 6.2, which is a formal technique of integrating different functions and figure out what the antiderivative is of that function. So in 6.3, we're going to look at definite integral. On the other hand, in 6.2, we mainly focus on indefinite integral. Okay, so the fundamental theorem of calculus, which is what we have here, says if f is continuous on the interval from a to b, and capital F of x is an antiderivative of f, then capital F prime is equal to lowercase f. All right, so basically, when we integrate f, we will get capital F. All right, so f is an antiderivative of lowercase f. Okay. Now, one thing that you will see that's a little different from indefinite integral is that notice that we don't have the plus c here, right? We don't have the plus c in the fundamental theorem of calculus, and we will see with an example why that's the case. Okay. All right. So basically, this is what we're going to be doing. Right? All right, so let's look at example one. Compute the integral from 1 to 3 of 2x dx numerically and using the fundamental theorem. All right, so first, I'm going to copy down the questions, right? Like that, dx. Okay, so we're not going to worry about the bounds for now. We're just looking at the integral. Right? So first, what we're going to do is I'm going to put the 2 on the outside, right, like that. X dx. And the rule that we're going to use for integrating x is the adding the power and divide by the new power, right? So 2 multiplied by, so the original power is 1, right? So add 1 to the power, we get 2, and divide by the new power, which is 2, and then plus c, right? This is what we did in 6.2 when we're integrating. All right. Now, here is the notation that we're going to use that's a little different from indefinite integral to definite integral. Now, to definite integral, we are actually evaluating from 1 to 3, right? That's our a and b from 1 to 3, right? So we're going to put the lower bound down here, right, on the closed bracket, the lower part of the closed bracket, and then 3, the upper bound on the top of the closed bracket. Okay, so that notation allows us to, or reminds us to evaluate whether the function is at 1 to 3, right? And actually, what we integrated here, the x squared over 2 plus c, that is our antiderivative. Oh, not exactly, actually. We're not done with the question yet. Okay. All right, so what we're going to do now is we're going to distribute the 2 back in. Right, so 2 times x squared over 2, we get x squared. And 2 times c, that's 2c, right? But remember, c is a constant, right? So 2 times c is just some other constant, right? So to make it a little simple, we're just going to keep writing it as a c, right? And let me make a little note here. So that is actually 2c, but since both c and 2c are constants, are, I should say, unknown constants, we just write c. Okay. All right. And then, of course, the close brackets to include uh, our bounds, right, from 1 to 3. All right. So this is going to be the extra step that we will do from indefinite integral, right? So this whole thing, x squared plus c, that is capital F of x, right? That is one of the antiderivative. one antiderivative of 2x. Okay. All right. And to move on, all we need to do is follow the fundamental theorem of calculus, which is on top here, f of b, capital F of b minus capital F of a. All right, so here we're going to do capital F of 3, right? That's our upper bound, minus capital F of 1, which is the lower bound, right? And let's see what we have. All right, so F of 3, that's just 3 square plus c, right? Minus 1 square plus c, right? So this one is capital F of 3, and that is capital F of 1. And from this part right here is going to be the fundamental theorem of calculus, right? Fundamental theorem of calculus, FTC. All right, and all we need to do now is just evaluate this, simplify it. All right, so we will get 9 squared plus c minus 1 minus c. Now, one thing you will notice is the c, they actually subtract each other out, right? Leaving us, oh, sorry, not 9 squared, just 9. All right, one thing we'll notice that c is gone and leaving us just 8. Right? And that is our final answer. Notice that the final answer does not have any c's in it, any plus c or minus c. Right, so this is one thing we can do. Right, the constants c are going to be eliminated in the process of a definite integral. Therefore, we can ignore it when evaluating a definite integral. Okay. So that's the case for definite integral, but keep in mind that if we are working with indefinite integral means when there are no bounds, we still have to add the c. Okay? It's only in the case of definite integral, whereas if the bounds are given to us, then we can drop the c's. Right? So we don't have to write the c in here, we don't have to write the c in here and in here anywhere. Right? All we care about is that the c's are going to be eliminated, going to be canceled or reduced when we perform a definite integral. Right? So to save some time, we won't write the c. Right? So for this example, I'm just trying to show you what happens to the c's when we're evaluating a definite integral. Okay, and that's our final answer, which is 8. Right? All right, here's another example. We're integrating from 0 to 1 of the function 8 times e to the power of 2t dt. All right, so this is integration. Let's go ahead and get started. First, let's bring out the 8, put it on the outside, e to the 2t. Now, to integrate e to the 2t, the technique or the formula that we're going to use for general e to the 2t is this. Right? Integral of e to the at is 1 over a times e to the t, e to the at plus c. Right? So this is for the definite integral, which we talked about in the last section 6.2. All right, so let's do that. All right, so to integrate this, we have e to the 2t, that stays the same, and then we need to multiply by 1 over a. So 1 over a is 2 in this case, so it will be over 2. Right, from 0 to 1. Now notice that I'm dropping the c here because we are working with a definite integral, and we know that we showed that in our previous example that the c from a definite integral is going to be eliminated, so we don't have to write it in this case. Okay, so let's multiply the 8 in here. We get 4 times e to the 2t, going from 0 to 1. All right, and 4 times e to the 2t, that is our antiderivative, right? This whole thing is our capital F of t. Right? And all we need to do is evaluate them using fundamental theorem of calculus, which is going to be capital F of 1 minus capital F of 0. And that will give us, when we plug in 1, we get 4 times e to the power of 2 minus 4 times e to the power of 0. Okay. Now, 4 times e to the power of 0 is just 1, right? This part is just 1, right? So we are really writing minus 4, right? 4 times 1 is 4, right? And that's our final answer. Now, if you want, you can actually factor out the 4, and whatever it's left will be in the parentheses. That will be e squared minus 1. A little nicer representation, but both of these will be fine. Okay. All right, our next example, example 3, is a little different. Right? From time to time, you will be given a question like this, where they don't give you the integral notation. They have a few sentences representing what we want to find, right? So let's look at this problem together. Write a definite integral to represent the area under the graph of f of t, which is e to the power of 0.5 times t, between t equal to 0 and 4. Use the fundamental theorem to calculate the area. All right, so this is the function that we're going to be integrating, right, f of t. And what they are telling us between 0 and 4, that's our lower bound and upper bound, right, a and b. Okay, so let's write out what the integral will look like first. Right, our goal is to calculate the area under the curve, right? So area is equal to the integral going from a to b, which is 0 to 4 from the question, of the function that is given to us, right? E to the power of 0.5t. And since in this case, notice that the independent variable is t, right? So we need to add the dt, right? Even though the dt is just a symbol, but it's still very important because the dt, this expression represents the end of the integral. All right, you can think about this. The integral sign is the beginning of the integral, and then the dt is the end of the integral. Okay, so always remember to write the dt. Okay, so that's the setup, right? That's how we set up the definite integral. It looks very nice. We have the integrand, which is the function we're integrating. We have the lower bound and upper bound, right? If you don't have a lower bound and upper bound, then it will be an indefinite integral. So usually, if it's a definite integral, the question will tell you what the bounds are, right? In this case, it's 0 and 4. Okay, and then you add the dt yourself. All right, let's go ahead and integrate this. All right, so we're using the same thing, right? It's exponential. That means when we integrate, we copy the same exponential function and then divide that by the constant a. In this case, the constant is 0.5. Okay. All right, and next we want to evaluate this whole thing, right? Because this whole thing is the one of the antiderivative f of t, capital F of t. All right, we want to evaluate that from 0 to 4. Okay, and I know the previous example we wrote down capital F of 4 minus capital F of 0, but you don't have to write that. You can write it, just evaluate this directly, right? So we can evaluate the function at 4 first. So we can write e to the 0.5 times 4 over 0.5 minus e to the 0.5 times 0 and over 0.5. Okay, and let's see what we have. All right, so first one, I have e to the 0.5 times 4, which will be e squared over 0.5 minus e to the power of 0, which is 1 over 0.5. Now, 1 over 0.5, if you have 0.5 in the denominator, that's actually 2, right? So we can write this as 2 e squared minus 2. And just like the previous example, if you want, you can factor out the 2 and write it as 2 times e squared minus 1, making it a nicer representation. And again, both of these are fine. Okay. And let's look at a picture that represents what we have found. Right? So here we have the graph of e to the power of 0.5, and we are looking for the area under the curve between 0 and 4. So essentially what we have found here, 2 times e squared minus 1, is the light blue area that's under the curve, where t is between 0 and 4. Okay? And the shaded area is what we have found. All right, the last type of integral we're going to talk about in this section is called improper integrals. All right, and so improper integrals is a type of definite integral in which one or both of the limits of integration or the bounds of integration is infinite, or the integrand is unbounded. Okay, so one example would be like going from negative infinity to 1, right, of some function, right? Because the lower bound is negative infinity, that makes it an improper integral. Or if we have like a 0 to positive infinity of some function, that is also another type of integral, improper integral. And also you will get, from negative infinity to positive infinity, right, of some function. That so there are many types of improper integrals, and we are actually just covering like a few of them in this section. Now, don't worry, we're not going to learn how to evaluate improper integral in in this part, but we do want to know how we can estimate an improper integral. Right, so let's take a look at an example together. All right, so here we have example 4, interpret and estimate the value of integral from 1 to infinity of the function 1 over x squared dx. Now the integral represents the area under the curve of 1 over x squared from 1, x equal to 1, and infinitely far to the right, right? Because the upper bound is infinity, right? It looks like a sleeping 8, right? And here's a figure to show you what we're looking at. Okay, so we're looking at the area under the curve of 1 over x squared, and starting from 1 and to the right and non-stop, right? And we know that um, for the function 1 over x squared, as x gets very large, the function value is getting very close to 0, right? So when we are looking at very far to the right, the function value is the area under the curve is close to non-existent, right? Very close to 0, right? So after a certain point, it's not going to matter um, what function value we're looking at, or the area under the curve, right? Um, but it's going to be a little technical if I if we go too deep into how to evaluate improper integral. So here we are going to do a few estimation. Let's say I'm just going to take the integral from 1 to 10, right? 1 to 10 of 1 over x squared dx. Okay, and let's try to evaluate this integral by hand. Okay, so first I'm going to rewrite that as a power function. So 1 over x squared, I can rewrite that as x to the power of negative 2. Right? Now that we have a form of x to some power, we can integrate this by using the simple power rule, which is adding 1 and divide by the new power. All right, so if I add 1 to negative 2, the new power is going to be negative 1, and then we divide by that negative 1. Okay, and then don't forget, we want to evaluate this from 1 to 10. Okay, and let's see what we have. Right, so basically we are evaluating negative 1 over x going from 1 to 10, right? That will be negative 1 over 10 minus negative 1 over 1, which will be negative 1 over 10 plus 1, which gives you 9 over 10. right? And then in decimal, that would be 0 0.9. Okay, 0 0.9, right? That's a nice number. I mean, it's not too crazy or anything like that. And let's see what happens when we integrate from 0 to 100. Right? Now, if we change the integral from 0 to 100, 1 over x squared dx. Now, we actually did the integration part already. We know it's negative 1 over x going from 1 to 10, but now we're going to go from 1 to 100. Sorry, it's not 0, it's 1. Right? So let's see what we have. We have negative 1 over 100 minus negative 1 over 1, which comes out to negative 1 over 100 plus 1. And that gives us 99 over 100, which is 0 0.99. So you can see that as we take more x value, right, the value is a little different, but we can see that it's actually going somewhere else. Right? Let's do one more. And for this one, I'm just going to show it to you. When we integrate from 1 to 1000, right, we actually get 0 0.999, which is very close to 1, right? We're starting to see a trend here that the larger x value we take for the upper limit of integration or upper bound, the area under the curve is getting very close to 1. And that is actually a really good estimation from taking different x values like what we have been doing here, to show that the area under the curve of this improper integral actually goes to 1. Now, since we're just estimating, we can say that, okay, these calculations suggest that the upper limit of the integration tends to infinity, the estimate tends to 1, right? The larger upper bound we take, the closer um, the value is going to get to 1, right? And we're not going to go into details on how exactly we can show that this improper integral actually goes to 1. And if you're interested in that, that will be taught in the regular calculus class, in which we're not going to go into too much details here. Right. So something a little interesting. So we don't actually say that the area is equal to 1. We say that the area converges to 1. Right. So we say that the improper integral converges to 1. Right. Now this word converges is used a lot in Calc 2, right? And when we go in, if you are interested in changing your major to math, then that's one thing you will see a lot is talking about converging, convergence, or converge. But for now, we are not going to worry about it, right? Um, and that is how you can estimate an improper integral, right? If it's to positive infinity, you can take 10, 100, 1,000, 10,000. Or if it's negative infinity, you can do negative 10, negative 100, negative 1,000, and see if you can see a trend of what the value of the integration tends to. All right. And that will be all for today. That is 6.3. And thank you very much. I'll see you next time.